Welcome to this video on the topic of advanced trigonometry. In this video we'll be having a look at the unit circle and the idea of symmetry around the quadrants of the unit circle. Now, reviewing what the unit circle is, the unit circle is defined by having a line of 1 unit in length, fixing one end of the line to the origin of the Cartesian plane, and then swinging the outer extremity of the line through a full sweep of 360 degrees, so theta being 0 all the way up to 360 degrees. Observing what that looks like is we end up tracing a circle which we define as the unit circle. Now in this video today what we're going to be observing is, or what we're going to be trying to understand in a bit finer detail, is the geometry of the circle that gets traced at as we build this unit circle model, as we can see here. Now starting off, we're going to have a look at the first quadrant here. What we find is that when we sweep our angle of interest theta from 0 degrees all the way up to 90 degrees, we end up drawing this nice looking triangle here, where the angle of interest theta is interior to the triangle, and this purple line over here, so the length of this purple line describes the y coordinate, and this length of the green line here describes the x coordinate. So this is the first quadrant. Now if we sweep over to the second quadrant, what we find is that it looks mostly the same. However, there's some slight differences to the model itself. So the first thing you're going to notice is the triangle. It's no longer pointing outwards to the right. So over here it's pointing outwards to the right. It's now pointing outwards to the left. Secondly, what we find is that the interior angle of the triangle here is no longer explained in terms of theta. Rather, theta is now external to the triangle itself. So observing the first quadrant, theta is internal, and theta itself describes the geometry of the circle. However, over in the second quadrant, theta is now external, and we don't have anything that describes the interior angle of the triangle. So those are the 2 points. The triangle is a mirror image about the x-axis from observing the y-axis here, and the angle theta no longer describes the interior angle of this triangle. Now moving down into the third quadrant, we get some slight differences again. So now theta itself is internal to our triangle that we're using to describe the location on the outer edge of the unit circle here. However, it's much larger, so it's both internal and external to the triangle in that part of theta is external and some of it is internal. So once again we find that we no longer have an angle that describes the interior of the triangle. And more so, the geometry of the triangle is different to the first and the second quadrant. So in the first quadrant, the triangle is pointing up and out to the right. In the second quadrant, it's out to the left and up. And then in the third quadrant, it's downwards and out to the left. So what you're going to notice is the triangle itself is a mirror image of the second quadrant about the x-axis. Now finally, looking at the fourth quadrant, we see a fourth and final configuration of this triangle. So theta itself remains external to the triangle itself. However, we don't have a value that describes the interior angle here. Furthermore, the triangle is also in a completely different geometric setup to the other 3 quadrants, so it's pointing out to the right and in a downward direction. Now what we're going to look at is how we can explain the interior angle of this triangle, and thus how we can determine the coordinates that are down here. So the coordinates that are explained when this hypotenuse here touches the outer extreme of this circle. Now to do this, what I've gone and done is I've created a second Desmos program. It's going to allow us to see these triangles itself in multiple quadrants at the same time. So if we jump over to this model here, what you're going to find, looking at the first quadrant only, as we scroll upwards, what we can see is that this red line here is going to represent our angle of interest, theta, and this purple angle in here, that's going to represent our interior angle of the triangles that we're looking at. We're going to call this interior one here phi. So we've got theta in red and phi in purple. Now moving along in the first quadrant, this is something we're quite familiar with. We've been working with this or these sort of measurements since year 8. But now what I'm going to do is I'm going to scroll it all the way down to 0 and I'm going to turn the second quadrant on. And what we're going to observe is the same triangle in the second quadrant as we're looking at the first quadrant. So as we start increasing theta, what you're going to find is that in the second quadrant, we have the mirror image of what's going on in the first quadrant. So the first thing you're going to notice is that as I increase the value of theta, the triangle on the left here, it's starting to grow. But more interestingly, the value of theta that defines the triangle in the second quadrant is decreasing as the value of theta in this first quadrant is increasing. The reason for this is the value of theta here is the same as this interior angle, so phi, of the triangle in the second quadrant. And secondly, you see that there's symmetry about the y-axis here. So that's the second quadrant. Now we're going to have a look at the third quadrant and compare the third quadrant to the first quadrant. So comparing the first and the third, what you can see is that as the angle theta increases, so does the triangle in the second or third quadrant over here. So the triangle grows as theta grows. Furthermore, what you can see is that this value of theta here in red, it's also combined with this purple line in here. So as the triangle grows, the value of theta grows. Now turning off the first quadrant and turning on the second quadrant, what you're going to see is that the second and the third quadrant, they're mirror images of one another. Now we'll turn these two quadrants back off and we'll look at the first and the fourth quadrant together. So observing the first and the fourth quadrant, what we see is that as the angle theta increases, so does the size of the angle defining the triangle in the fourth quadrant over here. So as theta increases, so does the triangle in the fourth quadrant. However, the value of theta in the defining the triangle in the fourth quadrant is decreasing. That can be seen with the red line defining in here. So what we're able to see with this model is that there's symmetry about the unit circle, but more so we see that the interior angles of the triangles that we're interested in, they're all defined differently, or they've all got a different relationship to the angle theta. So as theta grows, the triangles change in different relationships. Now let's have a look at some of our notes and we'll see if we can try and explain the relationship between theta and the interior angles of the triangles that we see in the first, second, third, and fourth quadrants. So what we can say is that in terms of symmetry about the unit circle, as the angle theta sweeps about the unit circle, triangles of differing but similar characteristics are formed in each of the four quadrants. This is defined, or this can be seen in the diagram that we have over here. Now moving down, the quadrants of 2 and 3 are mirror images of quadrants 1 and 4 about the y-axis. So quadrants 2 and 3 are mirror images of 1 and 4 about this y-axis here. Furthermore, the triangles of quadrants 1 and 2 are mirror images of quadrants 3 and 4 about the x-axis respectively. So 1 and 2 are mirrored about this x-axis in 3 and 4. So as the triangle in quadrant 1 grows, so does the triangle in quadrant 4. As the triangle in quadrant 2 grows, so does the triangle in quadrant 4 or quadrant 3. However, the only difference is that they grow in the opposite direction. So as one grows up, the other grows down. So they're mirror images. This pattern holds true by observing the interior angle of interest, so phi, within each triangle. So phi itself is the interior angle of these triangles. Now what we're going to do is, if we go down here, I've got different models showing the relationship of the triangles, or the relationship with theta and phi, for each quadrant of the unit circle. So over here we have quadrant 1, quadrant 2, quadrant 3, quadrant 4. What we're going to do is we're going to define the relationship of the interior angles with respect to the angles theta. Now, observing the relationship, the line in red, that is defined as theta, and the line in blue, we define this as phi. And for the first quadrant at least, we find that the value of phi mimics the value of theta. So we say phi is equal to theta, and we can say that phi and theta are equal. Secondly, in the second quadrant, what we see is that theta is defined by this red arc over here, and similarly phi is defined as the interior angle of the subsequent triangle in the second quadrant. What we can see is that phi is equal to 180 degrees, take away the value of theta. So from that we can say that theta and phi sum to make 180 degrees. Furthermore, phi is external to theta. So that's quadrant 2. Now looking down to quadrant 3, the relationship is different once again. We see phi is still internal, because it's always going to be internal for this, but theta is both internal and external. So what we find is that phi can be described as equaling theta take 180 degrees. So phi and theta, or you can see theta is a combination of 180 degrees, so quadrants 1 and 2, plus the value of phi in there. So phi is equal to theta minus 180 degrees. So phi is external to 180 degrees. And similarly, phi makes up the portion of theta above 180 degrees. Alright, so that's the third quadrant. Now the fourth quadrant, we have the final arrangement for this triangle. So what we can see is that phi is external and theta is all the way around, so it's also external. Phi is internal, I should say. Now phi can be described as 360 degrees take theta. From that we can say phi is external to theta, and secondly phi and theta sum to 360 degrees. So what we can see here in this diagram is the foundation of what it is we're setting out to understand in this particular video. So what we're looking at is the relationship of the interior angles of these equivalent triangles as phi, or as theta, moves around the unit circle here.